Ladies and gentlemen, good evening. My name is Marshall Dallas and I'm the Chief Executive of the EICC here. And I'd like to welcome you to Chapter 1 of the EICC's InovationNation series. Innovation has become quite a watchword at the EICC over the years. So it's a pleasure and indeed a privilege to see so many of you here who truly epitomise the meaning of the word innovation to its full extent. I would firstly like to qualify why the case of the EICC, that innovation has become such a watchword. Notwithstanding the unique features that our venue has at its disposal, such as moving floor technology and revolving auditoria, which you're all in this evening, the true essence of innovation is captured through the thousands of events that have taken place here over the last 2 decades and attracted more than 1 million delegates from all around the world. Many of those individuals are highly respected in their field or thought leaders representing a wide range of academic, scientific and business disciplines. The cross-fertilization of ideas generated through such conferences leads to the kind of advances that can have positive, far-reaching effects to the development of new vaccines or innovative new technologies to improve the lives of millions. A conference, congress, symposium, or whatever you may call a meeting of minds is about engaging and inspiring an audience. And the best way to achieve this is through fresh, innovative ideas. Edinburgh is a city that's always punched above its weight in terms of innovation, with recognised strengths in the innovation-based economy for which it's internationally known. It was therefore fitting that between 2011 and 2013, EICC and Edinburgh was fortunate to have hosted TED Global. TED Global is a celebration of human inventiveness, exploring ideas, innovation and creativity from all around the world. It was very much the catalyst that inspired the InovationNation concept and a case in point of how an idea can inspire and lead to something else. We're therefore delighted and honoured to welcome so many highly respected academics who have given up their valuable time to present their ideas to us through the InovationNation seminars. We look forward to hosting them all here at the EICC, beginning this evening with the theme of energy. It is our intention through InovationNation to engage with individuals, organisations, and the future generation who we hope will promote Edinburgh and the EICC to even more thought leaders from across the globe. The effects of bringing international conferences to Edinburgh are far-reaching, including promoting inward investment opportunities. Not only do we see this as a means of cementing EICC's global reputation, but the status of Edinburgh as a centre of academia and scientific excellence. So once again, ladies and gentlemen, welcome to the EICC. I hope that you all enjoy this evening. And I'd now like to introduce the internationally acclaimed innovator, Director of Biofuel Research Centre at Edinburgh Napier University and Founder-Director of the award-winning Celtic Renewables, Professor Martin Tangney.
Hi. Just waiting for some slides to appear. Okay, here we go. Thanks for the introduction. It's really good to be here. I've attended some fantastic events in this venue. It really is state-of-the-art and an exquisite place to come. I encourage you all, if you're running events, run them here. And if you just want to attend an event, come here. It's really good. The food's particularly good, but that's another thing. So the theme for this evening is renewable energy. When people think about renewable energy, they think about climate change, global warming, carbon emissions, drastic changes in the weather. And all of this is about the effect that carbon is having on the climate, which is fine, that's true. But to pigeonhole renewable energy in that one very important dimension is to miss a lot of what it's also about. The area I work in is in biofuels. In America, their drive for biofuels is dominated by their need to become energy independent and have security of energy supply, not so much about carbon emissions. And the other inescapable driver, we heard it all through the referendum. What's going to happen to Scotland with the North Sea oil, all the rest of that? Because oil's running out. People know this. It's a fact. Oil is a finite resource that we're digging up and we're burning, and it's going to disappear. So for all of these reasons, carbon emissions, energy security, and a need to reduce our dependence on oil, there is a strong and consistent drive around the world to introduce alternative forms of energy. In terms of oil specifically, our energy consumption here in Scotland, in terms of using up oil, is actually in transport. That's where our dominant source of using oil is within the liquid transportation sector. And it's not just Scotland. Scotland's part of the EU still. And here, we're mandated. The EU has said we must produce 10% of all of our fuel by 2020 must be biofuel. Now, there's some internal debate in the EU about this, but there's internal debate in the EU about most things. But it is a law. And why? Why biofuel? Why is that an alternative to fuel? Well, what we currently do is we take the oil reserves that are buried under the ground and we dig them up. Do it off the North Sea. We dig up the oil, it's buried under the ocean. We convert that into a fuel molecule, which we're able to burn in the cars, and that powers our engines. But that releases carbon dioxide into the atmosphere. Now, that carbon dioxide will not go into the atmosphere unless we dig up the oil and burn it in the cars in the first place. What happens in nature is carbon dioxide is naturally taken up by plants. It's absorbed. They breathe in carbon dioxide and breathe out oxygen. We do the opposite. That's what keeps the whole world going. And that carbon in the carbon dioxide becomes part of the plant material. So the premise behind sustainable biofuel is, can you take the carbon that's embedded in the plant material and convert that into a fuel source so that when you burn it, you're simply returning the very same carbon dioxide back into the environment. You're recycling the carbon dioxide rather than putting virgin carbon dioxide back up into the atmosphere. To all intents and purposes, we're putting more recently dead plant material into the car, because oil is just dead biological material. It's been there for a very, very long time. There are some arguments, debates, and the media has been full of sustainable biofuel versus unsustainable biofuel. My focus is on sustainability, and a simple way to look at that is to find sustainable resources that you can use as your raw material to convert into your fuel material. I looked to see, as an expert in one type of biofuel, I thought, where can I find a source of abundant raw material, consistent and available, that I could tap into and create a biofuel out of that? And I turned to the whiskey industry, which has been around for hundreds of years. It's a traditional industry that will not change again for more hundreds of years. We've been making it the same way ever since the Irish taught you Scots how to do it in the first place. And we take the barley, you malt the barley, which means that seeds germinate, they produce natural enzymes that release some sugar. And then that sugar is washed off the barley, and it's fermented with yeast. So they're the only ingredients, barley, yeast and water. You make a beer in these vats, and then you distill off the alcohol from that beer. And that's always done in these old-fashioned traditional copper stills, and there's lots of good reasons why they use the copper stills. The alcohol is then fermented in warehouses for legally 3 years and 1 day, but you know the fine Scottish whisky is often there for 8, 10, 12, 20, 25 years. And it's that maturation, actually, it's a totally different lecture, but that maturation in the barrels is what imparts all the flavour and the colour and the characteristics to all the multitude of, I confess, really good Scottish malt whisky that's produced in this country. But in addition to the whisky, which in many places is less than 10% of what actually comes out of your distillery, you're left with all that residual barley. All you've taken is the sugar out of it. And that poses a disposal problem to the industry, the solid barley material that's left over. But more problematically, when you distill off the alcohol in the copper vats, you're left with the liquid minus the alcohol. It's a non-alcoholic, incredibly awful beer. And it's copper contaminated, and that's at scale. So every year in Scotland, this is produced in our distilleries. There was 2 billion litres of this pot ale produced last year. So what I looked to see was, that's an abundant source of raw material that has no or negative value to the industry and poses a disposal issue in a country where the government is pushing very strongly for zero waste, sustainability, carbon emissions. And I looked to see, could I do something more sustainable with that residue. And so we worked in the lab as a research project, and the theme for the year being innovation. And we're looking to see how do you take innovation into industry. Well, we tried to combine the liquid, the pot ale, with the solid material, the draff, and create a new raw material that, analogous to the whiskey industry, we could then ferment that and make a different alcohol. And the process that we used is something we specialize in at the Biofuel Research Centre, which is a thing called the ABE fermentation. It's a 100-year-old technology. We didn't invent that. What we did was we adapted it in a modern day context and used an entirely sustainable substrate that had never ever before been tried. Why biobutanol? Well, a number of years ago, this is an alcohol and it was recognized, it was used in the chemical industry, it still is used in the chemical industry, that's what we use for today, but it's often made, or it's predominantly made from oil reserves. But as a fuel, it's got more energy than ethanol, which is a 2-carbon alcohol, and butanol is a 4-carbon alcohol, so it's got more energy. It's compatible with our existing fuel structure. We don't need to change anything in order to introduce it. We don't need to change the car engine, very importantly. You can put it in neat if you want to do, which is what the originator of this process, David Ramey, did. He put butanol in his car and drove 10,000 miles around America to prove that this would work as a fuel. You can even blend it with diesel. So you can make a biodiesel with no biological diesel component in there, but because you've added biological butanol, you've now converted that into a biodiesel. And it turns out to be a very, very good base unit for making jet fuel, and that's attracted the interest of all the major airlines. So this is a pretty good chemical to be using as your starting point as an advanced biofuel. Now, as I said, we know how to make this historically. I didn't invent that process. What we did was look to see could we do it in a very, very different modern context. Critical to achieving this was the funding mechanism that we managed to obtain from the Scottish Government, and it's through the Scottish Enterprise Proof of Concept Programme. Why this is so important is that if you take a technology readiness levels and adoption graph of here's something that's an idea, here's something that's a big booming industry. There are various levels that are recognized along the way that signify stages of development. What universities are very good at is the basic research. You will get an idea, you will do test tube science, figure it out in the laboratory, and that's 1,000,000 miles away from where companies come in and start building huge, big production facilities. There are funding schemes for university research projects, and then there's a lot of venture capital and other funding out there, equity investment, to build factories and to go ahead into mass production, because at that stage you reckon this is going to be economically viable and profitable. That gap in the middle is the problem. Bridging that gap is a difficult thing to do. For somebody to stick £100 million into a business because an academic has played around with a test tube or a Petri dish, it just doesn't happen. So this funding scheme afforded us the opportunity to take that interesting observation in the lab and build it up to the point where we could cross that bridge and enter into the world where this looked like an interesting industrial business proposition. But it's not all about the money. And in addressing the concept of innovation into enterprise, the funding gap is huge and real, and things like the proof of concept program that are designed to support this are invaluable. I can safely say, without that funding, I wouldn't be here today. But that gap is also occupied by other problems. There's a mindset gap. Not every academic wants to take their test tube science and build a factory, nor should they have to. Their primary role is to educate the next generation of people. But this is where these ideas are born. And how do you take those ideas through? They don't really want to cross the bridge. They don't want to build it all the way through. In fact, very often, what starts off as an idea for a research grant, where they go, I think I can cure cancer, I can invent never-ending electricity, if only I could do this little bit. And their research grants will be about doing that little bit, without any real notion or belief or interest in how they're going to build that bridge all the ways across to the point of adoption and sale and industry and new business and commerce in the country. It's not something of direct interest, and it's often clouded in the decision that's given to them to award the grant in the first place. And what you end up with is people taking interesting ideas and not building bridges, not crossing from the interesting idea to the commercial reality. They end up building piers. And they finish the research grant, and they'll get another research grant to improve the pier. And they will spend 25, 30 years in in a university working very hard and very well and doing really interesting things, but they will forever build a pier. It'll be a lighter pier, it'll be a faster pier, it'll have music on it, it'll be a beautiful colour, but it will forever be a pier. It will never ever go to commercial reality because that's not the focus, it's not the drive. There's also a silo mentality that can jeopardize taking innovation into action. And there's the old parable of the blind men going in to study the elephant. And one looks at the trunk and goes, oh, yeah, it's a snake. And someone looks at the tusks and says, yeah, an elephant is in fact a spear. Someone looks at the tail and says, oh, an elephant is a rope. And individually, of course, they're all quite right. It does resemble what they're analysing, but they're not analysing the whole picture. They're all only looking at the things that they're looking at. And this is where collaboration is an incredibly important and powerful tool. When you bring together people who can look at the tail and the tusk and everything and get the overview, the full elephant, if you like, and bring things to a complete reality. And this has to be real collaboration. It can't just be, well, let's get the best tusk analysts in the world and we'll have a fantastic idea of what a tusk is. It's not that. You need to look at the whole thing. And that's something that I think Scottish universities are actually getting better and better and better at. There's pooling agencies like the ETP and life sciences organisations where they're trying to pool the resources to go, can we get a view of the elephant? And even if we do achieve that, there is one other vital ingredient in here, and that's the mindset. To take an idea and bring innovation to reality, you need an entrepreneurial spirit. You need a different mindset. It's a different brain where you look at things in a different way to everybody else. Entrepreneurs want to build a bridge. They see the idea and they want to take it to commercial reality. And not all academics are entrepreneurial, nor, as I say, do they have to be. But an entrepreneur wants to do that. And for me, true innovation is building a complete bridge and not a short pier. So there's the pitfalls and the dangers and things you need to get through, but Scotland has a history of innovation. And some of the greatest inventions have come out of here. And I had an idea, and I wanted to take mine through. I wanted to build the whole bridge. So I set up the Biofuel Research Centre a number of years ago to try and support businesses and industry, and it really was focused. I have an industrial background, and I wanted, from the day I did the original experiments, to see a factory somewhere. It wasn't about perfecting one little bit of it. I wanted the whole thing to go. And so working in the Biofuel Centre, we took our Scottish Enterprise funded project and brought it to the point where it was ready for commercial adoption. And then we set up a company called Celtic Renewables, which took what was original research and then into a proof of concept and then ready to go to commercial reality. And it always had to be a company. The university had served its role and I'd gone as far as I could in that environment. So I founded the company a couple of years ago. In all enterprises, whatever you're doing, you need good people around you. So I was very, very fortunate that the chairman who agreed to come and take on this new adventure with me is Doug Ward, who's a pioneer of the biofuel industry, incredibly well respected. He got a CBE for his services to the livestock industry, which led to the BSE crisis, taking animal fat and taking what was, BSE contaminated animal fat and converting that into biodiesel. He set up InovationEnergy, which some of you will be familiar with. And that gave me massive gravitas and credibility to have him on board. One of the other problems in innovation and universities taking an idea through to commercial reality is that very often the academic who's come up with the idea is then tasked with running the business, which does two things that are completely mad in my eyes. One is someone who is an innovator within your university, who is capable of seeing to the other side of the bridge, has now been taken out of the environment. You've asset stripped your own university by putting them into the business. Secondly, you've taken someone who's a good innovator and you put him into a job where he's probably not qualified for it, and you've taken a good innovator and made a bad manager out of him. And that's, again, counterintuitive to me. So one of the first things on my list was, I didn't want to leave the university. I worked part-time for both. So the university has kept me. But secondly, I knew enough to know I didn't know enough how to run the business. So I got in Mark Simmers, who's here tonight, and Mark's been a gold mine for us in terms of running the business. He brought his business experience. I didn't wake up one morning with 25 years of business experience. And neither did he. He earned it. And he's been worked his weight in gold, metaphorical gold, Mark. You're not paid that much. Worked and made in gold to the company. And then the investment. We were also extremely lucky that we got stakeholder engagement as our investment. An individual who's a business angel, rather than a representative of a venture capital company. And he's in for the long term with us, and he's as much a mentor and great crack with us when he's out there. And that's been fantastic for us because it provides such stability to the company that we're allowed to get on with the job. And so it became a commercial reality in 2012 when our Energy Minister, Fergus Ewing, and the head of Chief Executive of Scottish Enterprise, Lena Wilson, both took time out to come and formally launch Celtic Renewables, which was kind of a pivotal day for me. That notion in the lab in 2008, 4 years later, had become Celtic Renewables. And then we told the world about it, and the world loved the idea. Every major television channel from London to Tokyo has been in to film the story and learn about the crazy mad Irishman playing around with Scottish whiskey and making this fuel out of the whole thing. Not everybody took it as seriously as you can imagine. We saw all the drink driving jokes and the one for the road and all that sort of stuff. We got it all. But a lot of people did take it seriously. And we were very lucky to win a multitude of cross-sectoral awards. And that's really important because it shows you span different sectors, from innovation through to the Shell Springboard, investor awards, the Green Energy Awards, which is held here. We won there. Environmental Sustainability Awards, chemical industry, they were involved in it. The automobile industry itself has given us awards and endorsed what we're doing. And it's because it impacts on all of those sectors, and they've all recognized that we have a role to play and that what we're doing is of value to them. So how is one lone academic, even blessed with a great board, going to bring it to reality? Well, I have a bunch of P's here for you. One is partnership. An important partnership for us was with Tullibardine Distillery. That agreement allowed us access to their raw material, which of course is critical. We can't do any analysis and testing and scaling up unless we have enough raw material. But it's a real partnership. We learned more about their pains in the industry, how they view these residues and effluents, and what value we can genuinely bring to them. And we understood the whisky industry an awful lot more through working with them. And using that raw material, we partnered with the Biobase Europe pilot plant facility in Ghent. This is a state-of-the-art facility in the Canal Harbour area, which is a biofuel hub in Ghent. And in there, we had access to large-scale, pilot-scale industrial fermentation facilities, plus the team. Again, the people in there are fantastic. And I was one of the guys you could phone at 3 o'clock in the morning. He's probably half asleep on the floor, still working away on stuff for us. And I send our team over there, and they do the same thing over there. But it allowed us to scale our technology up from lab scale at state-of-the-art equipment. And it's people. People are the most important thing for me in what we do. Kenny, who's here, is one of those guys who's gone over to Belgium and kept the whole thing going. Kenny was in the original lab team that developed this and is an inventor on the patents that underpin the entire company. And he stayed with the company and got into it and brought his experience in technology and background into the whole thing as a stalwart of the business and as our lead scientist. This young lassie is very interesting. Eve, when I used to lecture in the university before I set up the Biofuel Centre, Eve came in as a student. She came in as a mature student on an access course because when she was younger in school, she was branded as thick and lazy. She then later found out that her thick part was she had dyslexia, and the lazy part is she's got this rare sleeping disorder called narcolepsy. She can't control her sleeping patterns. And then she got medication and help and assistance along the way, and she became the first person to graduate with a PhD from the Biofuel Centre. I'm very proud of her. She's one of the brightest scientists I've ever come across who could have fallen away by the system, but she didn't. She stuck with it, and she's now our head of research and innovation. So it is about people. People are the most important thing in any business. The famous Apple quote, which I won't say because we're going on the web. People, and of course funding, right? You can have all the people in the world, but if you can't pay them, it's kind of difficult. So yeah, funding is very important, and we've been very lucky. We've attracted significant private investment. Donald Houston, as I mentioned, and also our chairman has also put money into the company. And that's allowed us to leverage match funding from a bunch of other organisations who support us. Notably, the Scottish Government have various arms, like Zero Waste Scotland has given us a lot of money, and Scottish Enterprise. We also won a Shell Springboard Award. Most recently, we've been running a £1 million Department of Energy and Climate Change project funded by Westminster, and that's been very, very important to us going forward. So funding is kind of critical to the whole thing. The reason that the people have come and the partnerships have been formed and the funding has followed is because the proposition is simple. And any innovator who wants to take their idea to commercial reality must have a simple proposition. And ours is pretty basic. What we're doing is we're taking something that's essentially a problem and we're alleviating it. We're reducing national carbon emissions, we're providing environmental sustainability, and we can provide local solutions. So, for example, if you take the island of Islay, 8 iconic distilleries on that island, which is a remote and often inaccessible part of the country. If you take all of the effluent that's produced there and you process it locally on site on the island, you're solving local fuel problems. It's the most expensive fuel in the country. You're reducing transport emissions, you're providing local sustainability, local employment, and local energy security. When the boats can't dock, when the weather is bad in the winter, the lights go out in this place, you know? So you're providing local energy security. It's not just the great save the world thing, it's local as well in what we're doing. Having said that, the other key thing about all innovation is by definition it's new. So it's all about potential. And in our case, our first target is the Scottish malt whisky industry, but there's a broader potential we're going to look at. There are other countries in the world that make whisky. Obviously not as good, because I'm in Scotland, but Ireland, Japan, Canada, Australia, America, India, there are huge whisky-producing countries all over the world, and other related industries that we're also looking to tap into. Again, this is not an original idea. Let's look at waste residues and convert them into fuel. The man who gave us the car, Henry Ford, a fellow Cork man, was born 25 miles away from where I grew up in Ballinhassig. His cars actually ran on ethanol. He was the first bioethanol producer, the Model T Ford car. And he actually wanted to have bioethanol all over the place, but Prohibition came in and curtailed the production of alcohol per se in America. And had that not been the same, we might have a very, very different fuel mix today. But his vision back then was to build a car and fuel it with bioethanol because he believed that there was fuel in every bit of vegetable matter that we fermented. 90 years ago, he said that to the New York Times. We're simply trying to carry on that kind of ambition and that kind of dream. And a fundamental ingredient, my last P for the evening, that allows this and anything else to achieve fruition and is epitomised by the innovation that we've seen in Scotland over hundreds of years and that I'm sure we'll continue to see for the foreseeable future. The one thing that dominates everything for me is passion. If you believe in your ideas and you know that they can work, well, you got to believe in them because if you don't, nobody else will. But it's passion that brings it all forward. So if you believe in your idea, you have the passion to bring it forward, you get the right people around you, get the right support, bring everybody with you. You can make it work because this is an innovation nation. Thank you.
Thank you very much, Martin, for the truly innovative talk. Ladies and gentlemen, it gives me great pleasure to now introduce the CEO of FloWave TT, the University of Edinburgh's Ocean Simulator Facility for Marine Technologies, and recent winner of the Best Innovation category at the 2015 Green Energy Awards. Ladies and gentlemen, please welcome Mr. Stuart Brown.
Thank you. Good evening, everybody. Thank you very much to Alice for the opportunity to come and speak here today. I'm going to take you through a little bit more technical about FloWave. So we'll concentrate on some of the engineering here. FloWave, as Dallas has said, is a subsidiary company of the University of Edinburgh here. If I follow on from what Martin said, this is the idea of academics, and I'm the CEO who's been brought in, and hopefully I can demonstrate a little bit of passion about what we do, because I was convinced it's a major contribution to offshore renewable energy. So when we talk about clean energy from the ocean, we're not talking about oil and gas. I suppose if we take a step back, you can look at what we think of as lump energy and kind of deliver itself energy. So renewables is generally not lump energy, and it's generally the kind of energy that delivers itself. So you don't generally have a a problem with security of supply, because no one can stop the wind, no one can stop the waves. There are 6 types of green ocean energy, and the ones here that we'll skip through just for the purposes of illumination. There's offshore wind, which you may be well familiar with. It's kind of an offshore version of onshore wind. There's tidal, there's wave, and then we have sort of ocean thermal and salinity gradient, and then also tidal range. If you've heard about what's been going on with the Severn barrage, or rather the Severn lagoon project, as it's now converted to, that's tidal range. I'll just skip in to just explain what the other ones are. Ocean thermal is using the temperature difference in very deep water compared to high level water to drive a cycle which produces energy. And that's very good for places like Martinique, Réunion, Guadeloupe, and other places where you have an island with a high demand for air conditioning because of tourism, and also but a small population base, and no desire for wind because of the sort of the visual impact. And then the other is salinity gradient, and this is particularly where you're looking at the outflow of a river into the sea, and you can use an osmosis type process or reverse osmosis process to use that difference in salinity to generate current, electrical current. On tidal range, usually means a big barrage. The 2 images here are, one is in South Korea, and the upper one is in La Rance in France. But there are sites around the world, but there are not very many that actually work very well. And a part of this is because obviously you've got this barrage, and as the tidal range outside goes up, the water flows into the constrained area and then is trapped, and then as you wait for the tidal sort of tide outside, once you close the gates, to drop, then you've got that head difference, and the water flows from the high place to the low place. You can generate energy from that. But it's not the best place, or necessarily there's not many places where you can do that kind of technology. Where FloWave operates is really in offshore wind, in wave and in current, and I'll go into a little bit more detail about those just now. So with offshore wind, it's quite well developed and quite a mature industry. We have 4 gigawatts of offshore wind installed in the UK, and Germany earlier I think this week or last week, just hit 1 gigawatt installed. So that's a lot of power already coming from offshore wind. The UK leads the world in that, but most of that wind is fixed to the seabed in up to about 30 meters of water. When you go beyond 30 meters of water, the cost of the substructure and everything becomes a little bit heavy, or rather the structure becomes heavy, and then the cost goes up. So once you get beyond about 50 meters of water, floating wind becomes quite attractive from a commercial perspective. So FloWave, being a tank, an ocean tank, and I'll explain a little bit more about that in a moment, is quite well suited for floating wind, as well as its 2 original kind of academically driven goals, which was to be the best tidal tank in the world and the best wave tank in the world. So if we look at tidal current, what we've got here is the tide. Just to take a step back and explain it, what happens is that between the Earth and the Moon has a centre of gravity of the 2 bodies, which isn't in the middle of the Earth. And what happens is that sucks a bulge of water towards the Moon on one side, and then where the gravity is weakest, away from the Moon and this centre, a bulge on the other side. And underneath that, the Earth rotates. And that's why we get 2 tides a day, because the Earth rotates underneath those 2 bulges. When you look at that from a particular point of view of a location like Scotland, particularly where we as a nation of the UK is an island off of a continent surrounded by water, and you take that one step further and you've got a bunch of islands off of that island and archipelagos. When that tidal current is pushing to try and get past and around the island to the other side, from the Atlantic to the North Sea, it gets squeezed in between the islands, and when it gets squeezed, it accelerates and gets up to some very fast speeds. And of course, you're looking at large masses, like millions and billions of tons of water moving through a channel very regularly, fully predictable. If I want to quote one of the developers, if my device lasts 200 years, I can tell you exactly what it will be doing at 4 o'clock on February the 15th in 2025. So 35, in fact, do my maths right. So it's entirely predictable. And the thing is, and what works well for the UK, is that timing of when the flow is happening is different all the way around the coast. So it might be intermittent. There's always going to be a time when you've got slack water and it's maybe not generating. But if you've got enough stations around the UK, then when it's slack at one place, it'll be flowing elsewhere. And so you can get a very smooth, sustainable supply. And it literally is billions of tons of water moving past our country. So we are absolutely blessed with resource in the UK. Between the UK and France, we have 80% of the entire tidal resource of Europe. 25% of that is just in Scotland. So the images here, there's a couple of different designs in the small boxes on the left. On the right-hand side is the first consented full-scale project, which is the Maygen project, which is going to be deployed up in the Pentland Firth between the north of Scotland and Orkney. It's around about 90-something 1 megawatt turbines. So that will generate a lot of energy when it comes on stream. So if we swap then to wave energy, you're probably, if you've been following this, you'll probably be aware that a Palamas unfortunately went into liquidation earlier in the year. Sorry, not earlier this year, it was last year. And Aquamarine Power, which is the Oyster, which is the top left image, have retrenched a wee bit in size, but they're still trading and still looking to develop their core project, which is already deployed up at Orkney, the same as Palamas. Bottom left there is a company from Australia called Tangney, and they're deploying quite a lot of projects out in Western Australia. That's working well for them. They've actually tested at FloWave, their next generation of their device. So with wave energy, Scotland is blessed also. Here's a map. The big one on the left is these are simulations from Magic Seaweed. Now, Magic Seaweed is a surfer prediction site, and it uses various buoys around the world to take that data and produce live forecasts for wave height. To give you an idea, black is off the scale as far as their model is concerned. So what happens is these hurricanes that we see building up in the Gulf of Mexico and coming up through New Orleans and the eastern seaboard of the US, they kind of lose their energy over the land, but they're still a fairly major storm. They come out through or past Boston, and then they come into the North Atlantic, and they kind of get pointed at Scotland. And the reason they get focused on Scotland is a mountain range in Greenland. So the weather systems really just point these ex-hurricanes at Scotland and the UK. And what you see there with that black, there's a buoy in there called K5. It's just under halfway between the north of Scotland and Iceland. And that was recording 18-meter wave. Okay, and that's the 20-minute average. So that means that the average wave height for 20 minutes was 18 meters. That's about as high as this auditorium. So you imagine the amount of energy in that wave. Absolutely huge. There's a resource map on the right-hand side from DEC, and that gives an idea of the kind of resource that we have here. You can't quite see it in Orkney, but there's a great resource up in Orkney, and obviously Shetland is a bit beyond the top of the map as well. So why aren't we out there doing it already, collecting all this wave energy? Those two images give a bit of a picture. With tidal, you don't get massive storms, if you like. You don't get a ramp up of energy density that's 10,000 times more energy than on a normal day. With wave, you can. And you can see that arrow on the right-hand side of the lighthouse. The lighthouse is in the Bay of Biscay in France. That lighthouse keeper came out to see what the buzzing noise was, which was the helicopter. And there's a series of still photographs. And in the last one, the wave's gone past and he's not there. But he did actually just go back inside. He didn't disappear. But it gives an idea, and you've probably seen other posters of lighthouses being hit by massive waves, so the huge plume that goes up to the top of the lighthouse. Those really aren't generating conditions. Those are survival conditions. And survival is one of the problems with wave, because you get a normal day, a challenging day, and an extreme day. And those are vastly different in terms of the forces that can be put into a device. So one of the ways you can get to understand these forces is to test models. You're probably all quite familiar with the idea of airliners being in wind tunnels and so on. So test tanks do that role. They perform the same kind of role, but you can test performance, refine performance, you can prove concepts, and you can de-risk, which is quite important for the finances of these projects. So test tank operations are good. However, most of the test tanks, in fact all of the test tanks bar one, and now two with FloWave, are rectangular. And I tend to be, if I use my, I haven't got my phone, here we are. I use my phone as a little demo. Rectangular tank, and you have wave makers on one side and then a beach, as it's called, on the other, which absorbs that wave energy so it doesn't reflect around in the tank and interfere with the study you're trying to complete. So you put your waves in from this side, and all they do is run down the tank in one direction. Now, the real world isn't like that. You don't get waves just in one direction. If you're on the west coast of Scotland or Australia, or in the Bay of Biscay or the South Pacific, you will have an Atlantic swell, Pacific swell, a Southern Ocean swell, which will be a long 20-second, big, long roller ocean wave. But that might have started a week ago, and the weather will have moved and changed since then, and a more recent weather system, more local to you, will have started up. Here in Scotland, it tends to be a northerly. So we tend to have, on the west coast of Scotland, a kind of a southwest or a westerly swell that comes in, started a week ago, and then a more northerly that comes in. And where those wave peaks and the wave troughs meet and combine, they reinforce each other. If you only tested in a tank that only has one directional waves, you haven't tested in a proper simulation of the real world. So FloWave addresses that problem, and importantly, is not rectangular, it's circular. And it's ringed with wave makers all the way around. So there's these wave makers not only generate waves, they also absorb them. So what we do is we turn electricity into water waves on one side. They travel across the tank, and we absorb them on the other side. And we use that electricity and recycle it back in. So we can make waves in any direction across the tank because we can change the direction of that. And I'll show you a video which explains how that works. Over and above that, or rather underneath that, we can push that water around as well. And we push and pull that water, it was much easier to see in the video, to create current in the tank. And the concept of FloWave was to be able to simulate anywhere around the UK continental shelf, which means we can simulate that 18.5 metre wave from K5, and we can simulate the high flows that they're looking to exploit at Pentland Firth with the Magen project. If I push that on, a few details about the tank: 25 metres diameter across, that's a little bit wider than this room, 2 metres deep through the centre section, 2.4 million litres of water. You want to put that in context, that's just a little bit more than the big pool at the Commie, for those of you here in Edinburgh. And we can push that water around at around about 1.6 metres per second, which when you scale up from our tank scale is about 14 knots. That's 2 knots faster than the Bay of Fundy in Canada, the fastest tides in the world. So although we're built for the UK continental shelf, we can actually simulate tidal current of anywhere in the world. Also, on that wave, the wave height we can create is 700 millimetres. That doesn't sound a lot, but when you scale that up, that's actually a 24 metre high wave. So that is a huge capability that we have, and that's a regular wave. If we change the timings, we can create freak waves where they join together and get those peaks and troughs that will break ships. So this is an animation which explains a little bit about how FloWave works. So circular tank, we've this access gantry that allows us to get on to the floor, which raises in the middle. We can send these sine waves down across the tank in any direction. They're absorbed on the other side. And the important thing about that absorption means that we can stop the test after we finish running. The tank settles very quickly. It's not like a swimming pool where you see it's all rough for ages and ages and ages. And then we can start up the test in another direction. So if you're coming here to do research at FloWave, this means that you can get a lot of tests done during the day. Our settle time between runs is about 2 minutes. In other tanks, it's about 20. If we duck underneath the water, we've got a little generic tidal turbine array here in the video. And you'll see the turbines are now turning into a new tidal direction. When you build an array rather than just a single device, you're going to have issues to do with wake, where the wake of one turbine is very turbulent. It's going to put lots of vibration and extra forces onto the turbine downstream of it, and it's going to have slightly less energy in it as well. Now, the way we create this current is we actually separate the tank into 2 volumes, above and below the floor. And we use these pumps. Each one can push about 6 tons of water per second to push and pull the water underneath the floor and thereby create this flow across the top of the tank. And by turning using the control system to steer this current, we can turn that current around in any one of 360 degrees of the compass. This is hugely important for array tests, and this is partly the reason why the tank is so large, is that you can then validate computational models about how much energy your tidal farm will produce. Perhaps most importantly, we can do that at the same time as waves. So we can run current and waves at the same time in the tank. And this is what makes us pleased to be able to claim to be the world's most sophisticated real sea simulator. So I'll skip through. The rest of this video is just credits. What does it look like for real? This is the engineering. There's about £5.5 million worth of engineering in the concrete hull. The concrete hull is about £1 million, and the building over the top of it is about £1 million. It's a very complex machine down there. We're all about testing and validating and taking the stages carefully. So we did some dry runs down underneath the floor. And you can see here an idea of how the pumps work. You might notice they're spinning in different directions, and every blade is spinning at a different speed. This is just because of its position around the circumference. Sorry, this is just a handheld GoPro of me. While we were filling, you can probably see 2 fire hydrants in the back there. 4.5 weeks to fill with 2 fire hydrants. And that gives you an idea of the size and scale of the facility. We did our first tests in April with a variety of different clients. We called them the shakedown clients. Good mentions to Albertern, based out in Lonehead, and to InovationEnergy, again another Scottish company with a tidal turbine. With those shakedown clients, we then moved on to more commercial clients, and we'll show some of those in video as well. We were officially opened by Amber Rudd, the new minister at the time. I think she was 2 weeks in the job for the DEC, the Department of Energy and Climate Change. And here in November, we were very pleased to win the Best Innovation Award. We were also shortlisted for Engineering Excellence as well, I should mention. So we were shortlisted in 2 categories, which in itself is a big achievement. But we won on the Best Innovation category. I'm told, unofficially, that it was the only winner that was a unanimous decision by all the judges. And that is particularly pleasing to us because this isn't just the best innovation in wave and tidal, this is the best innovation in all renewables. So it's competed for against wind, solar, biomass, Martin, sorry, and everybody else. So we're very pleased with that, and it's really a huge accolade. So this is what it looks like now. Give you an idea of the scale. Can you see, hands up if you can see someone in a high-vis vest? Okay, a few, right, well this should help. It's right over the back there, but hopefully that will give you an idea of the scale of the place. Some video now. This will show you the tank running. It's probably the easiest way. The blue disc in the floor is in the middle is a floor, which is a floating floor, a little bit like the learning pool at the commie, and it floats up. So we effectively bring the seabed to the surface. We can work on it, fix things to the seabed, and lower the seabed back down. The white ring around the outside of that contains all those pumps, and then on the outside of that are the kind of grey as a galvanized steel louvers that, or turning vanes as we call them, that allow the water to go down beneath the floor and come back up again. So what we'll do is we'll show you exactly what was in the video, which is us starting off and making some straight sine waves. In this case, they're travelling just across the tank from the zero direction, as we call it, the 0 point of our compass, a tank compass. And what you do when you want to make something which looks more like a real sea is you take these sine waves, and you put together a spectra of them, of about 1,000 different sine waves, different amplitudes and frequencies, and you mix them together. You end up with this one is called a John swap. So it's effectively the same as the North Sea, and it's been validated against the way the sea looks and has been measured by oil and gas platforms out in the North Sea. But you get other flavours as well, and if you have the right data, we can actually replicate and turn your buoy data into a site-specific sea. We can replicate your actual site in the tank. Now, if you look at current here, this is current flowing in the tank at 1.2 meters per second, so it's about 3/4 of our maximum operational speed. It's equivalent to about 10 knots. That's faster than anywhere in the UK. So the Bay of Fundy is 12 knots. The Pentland Firth is about 8.5 knots. Skip along, show you some of the things that have actually now been tested in the tank. This is a Rockland Scientific, a Canadian company based in Victoria. Again, it's spun out of the university, and it's a turbulence measurement instrument. It's about $30,000, and it's the size of a fancy pen that you might buy in the airport in Geneva. In here, it's been bolted onto what is quite clearly a piece of drain pipe. This is a project that we're working with this company at the moment. It's a joint call between Canada and the UK to develop this into a project, into an actual instrument. It normally sits on a thing called a micro rider, which is a torpedo really about this big with data capture on it and so on. They drop it off a boat in the real world, and as the device falls through the water column, it measures the turbulence as it descends, and then it pops up further away, and they collect it and get the data off. This is to develop a tank-size version of that instrument, such that we can then have one instrument that works in the tank and in the real world. So leaving out one little bit of uncertainty. So this is this Albertern wave device developer. Their device is called WaveNet. It's like a mesh that lays in the top part of the water column. They have a device installed on the west coast, off the coast of Edinburgh. And they brought their device here into the tank because they wanted to test whether it would generate more energy in multi-directional waves rather than single direction waves. This is a time lapse of their test here. You can see the floor up when we start the movie, and you can see here what they did with their test. So the device is laid out in the test. We lower the floor, we bring the wave maker paddles up, we throw some waves at it from one direction, we throw some waves back from the other direction. We look at this from above, you can see the bars of shadows moving across from left to right. And that is just the straight sine waves that we always do when we start off a test. In this one, we've got two sets of waves coming in, just again straight sine waves, but they're 45 degrees apart. So one is coming from left to right, and one is bottom left. Unfortunately, not the easiest to see, but it's a very interesting device, this one, and great for the west coast of Scotland for providing kind of low levels of power, not grid connected, to, for example, fish farms, to agriculture, to offshore platforms. Then we had another, this is Weptos. They were in on a European-funded program, Danish developer, possibly the most sophisticated model we've ever seen in a tank. I'm told it's insured for €100,000. That's just their model. They've been developing this for 7 years, and you've never heard of them. So they've been working very diligently in the background, and the full-scale thing will be deployed in Denmark later this year, I believe. We've also done some other work looking at kind of cross-cutting challenges. This is cable. One of the problems when you're deploying a cable on the seabed in a high current environment is the cable will move. And if it's scraping along the seabed and the seabed has a rocky bottom, it's going to get damaged and abraded. So we simulated a rocky bottom with several sheets of marine ply with the chuckies that you might have on your driveway embedded in epoxy. We've got a lot of equipment. We don't want the chuckies getting loose and destroying our machine. So they're epoxied in, and then we were able to run and flow current at that. And here's a view of that test. So the cable's going down to the seabed, effectively, the bottom of the tank. You can see how fast the water's moving on the tank, and we're just measuring all this stuff off the gantry. We'll move on from that to another video, or rather another concept. This is the Tidal Foundation. This is a thing called the sub-hub from a company called QED. They're based in Edinburgh. And the way this works is it's a sort of gravity-based foundation. It just stays on the seabed by its own weight. But it is a half duct. And in current flow, it works a little bit like the rear wing of a Formula One car. And the hydrodynamic force pushes it down onto the seabed. So the faster the current goes, the harder it is doing, harder work it's doing to stay in place. We put this onto a 6 degree of freedom load cell embedded flush in the floor. It's about £30,000 worth of load cell. And then we did a series of tests looking at the current going down the axis of the device, 5 degrees in steps off, around to plus 30 and minus 30 degrees, and then every 30 degrees around. So we had the full circuit. We'd even try and push this over sideways. The important thing about that is that the tide doesn't go out the same way it came back in. The bathymetry is quite different. Usually you're coming from, say, the Atlantic into the North Sea. So a big volume into a small volume. When you go back, it's different. You've got going from a small volume into a big one, so the impedance, if you think of it in electrical terms, is much higher. And also the bathymetry is different. And the third thing is that the moon is also moved around in its orbit, or rather, where the Earth is turned underneath that bulge. And so the gravitational pull on the tide is different too. So you will never get a 0 and 180 degree ebb and flood tide. They're always different. So if your device doesn't steer into that, you've got to know that it will still work when the inlet angle is 10 degrees off or 15 degrees off. So we did that with this test. And here we are, just a little video of the device on the floor going down in real time. What you can see there is that the air inside the device venting, just as we lower the device. I'll skip ahead, I appreciate time is running. And here we are with a fairly genteel current pushing into the device. Here, as we zoom in, you'll see that we're about 60 degrees off the axis of the device. It's a little bit tricky to see underneath the water. But you look at the turbulent surface of the water, it's quite glassy. That indicates a low level of turbulence because the water's actually moving quite slowly. When you speed it up, the turbulence gets worse. And that's what happens in the real world. So here we are, much faster test in the tank, down the throat of the device, as it were, and the 0 degree axis. As we zoom back out, you can just see how much water there is flowing there. And it may look, oh yeah, that doesn't look much different to a river, except we have perfectly crystal clear water. We can control exactly the direction and speed of the current, and the current has fully developed flow, fully developed shear and turbulence, and no bits in it, no fish, no lumps, no rocks, no bits of wood. And it's fully instrumented, so we have a variety of instruments down there as well that can measure exactly what that device is seeing. Now we come to a thing called the ultimate load case, which is where the insurers and the certification bodies are interested in. And here what we're doing is we're putting in a current at 30 degrees to the device, and we're going to then run breaking waves over the top. So this is wave over tide, the most challenging conditions if you're a sailor. And the waves get very steep and they break and they have a lot of energy. And then instead of being just a wave travelling through the water with the water not moving, when you get a breaking wave, the water is moving, and so it imparts a lot more force. So you can see the waves, they have to travel to try and catch up with the current, and the current kind of suppresses the waves a little bit. But there we are, we've got breaking waves directly over the top of the device. And that's with the current there at 0.85 meters per second tank speed. So that's about 8 knots. So it's Pentland Firth conditions, and then with a huge rolling breakover, it's more than 8.5 meters high wave breaking over the top as well. So FloWave, as I said at the outset, was effectively conceived as a test tank for examining technologies associated with wave energy and tidal energy, but it actually is a sea simulator. So we have applications in other areas, obviously offshore wind, as we've mentioned. We have the cable stuff that we've been working on, and we're working with new companies on that as well. We have subsea, which is using ROVs and autonomous underwater vehicles, underwater robots, to do things like corrosion inspection, cable inspection, scour inspection. And the control of that is very difficult, particularly with AUVs. And also looking at vessel design. If you're going to install a large project in a highly energetic environment, you need a vessel that can do that as well. And we have some other applications we haven't sort of started doing testing on yet, which are called marine operations. So these are things like heavy lifting at sea, where you've got a large structure being lifted by a very heavy and expensive crane. For example, a jacket structure for an offshore wind platform. So for summarize for FloWave then, we can make complex waves, fast currents, and we've done all of that and proven all of that. We can simulate those the normal, the challenging, and the extreme environments. And we can back that up with effectively a first-class instrumentation suite, one of the best in the world, and the kind of brains that go behind that. So it's not only the best equipment, it's the best brains. And those two things together get you the best outcomes. Should have gone to Specsavers. Can't really read the text on that one. So we are a research asset. We are funded by the Research Council, by the university itself, and by Scottish Enterprise. And we're funded as a national asset, national facility. And if I quote the EPSRC, a national facility of international importance. So we're expecting to see global clients coming from Japan, from Chile, from France, Canada, the US, Korea, Australia, and so on. So all of that is here, and all of it came from the ideas of a few crazy academics. So I shouldn't say crazy. Very bright, very intelligent, forward-looking academics who just wanted to push the boundaries that little bit further. And here we are, right here in Edinburgh, 2 miles away from here, just directly south, at King's Buildings. So not only do we have our team, which is very expert, very experienced in tank testing, but we have the backup of the whole of the School of Engineering and the Institute of Energy Systems at the University of Edinburgh, which has effectively a 40-year track record dating back to Stephen Salter in the 1970s. So I'm happy to take a few questions just now if there's any direct technical